I find myself that I have behind the schedule a lot. So, so I decided that I will not cover all of the lecture notes I wrote. So, but I will cover essential parts of each section in the lecture notes, and for you to self-study the rest of each section. Okay. Yeah, because that we have lots of topics to cover this semester. So, yeah. But if you have any question, just let me know. Okay. Such as the additional problems in exercise number 5. That so I think I will give a comprehensive solution, because that is one of the quiz problems, right? So I think you can learn something from the answers to that quiz problem. All right. So I have to move on to study the completeness of eigensystems. Okay. And the question is related to the convergence and representation theorem of trigonometric Fourier series in section number 1. Okay. If you remember that for the main theorem in section number 1, we studied the piece continuous function, right? And so that the trigonometric Fourier series generated by such a piecewise continuous function, that the Fourier series will converge. All right, it will converge basically every point. And it will converge to the original function at a point x if the piecewise continuous function f is continuous at x. Okay, so we have at least the pointwise continuity, the pointwise convergence. And furthermore, in later sections, we if the piecewise continuous function has further properties like has piecewise continuous derivative, then we have uniform convergence result, okay, for the trigonometric Fourier series. The other problem is if we extend piecewise continuous functions to square integral functions. Okay, so that would be members in this L2 space. Okay, and so we would like to answer similar questions. Okay, answer similar questions. So, and we know that for each square integrable function, there is generalized Fourier series, right? Generated by such a square interval functions. Okay, and with respect to an eigensystem of either regular or periodic or singular Sturm-Liouville problem. Okay, we learned in the previous section. Okay, and so we will have convergence problems, right? Again, okay. So So this section is trying to answer such a question. Okay, so let's state the problem and the answer of the problem carefully. Now, so suppose okay, so for a square integrable complex or real value function f on AB, right? It generates okay, a generalized Fourier series summation phi n with respect to an eigensystem phi n, okay, of a regular periodic or singular Sturm Liouville problems in AB. Okay, so this is so where the Cn is written by as we know, okay, it's calculated by using the interproduct. Okay, with respect to the weighting function of x. Okay, and we know the weighting function of x is from the Sturm Liouville problem. Okay. Right. Okay, so we know we have, and we also state some convergence and representation theorem for piecewise continuous functions. Okay, when f is a piecewise continuous function. Okay. All right. Now, in general, okay, in general, such a generalized Fourier series sum may not converge, right, at some point in AB. Okay, or even converge at a point x in AB, but may not converge to f of x. Okay. And we have, so if f is piecewise continuous, then we have given a series of theorem to answer the convergence problem and the representation problem. But if f is just a square integrable, because square integrable function may not be piecewise continuous, okay, in general. So so that we might have convergence theorem in terms of pointwise convergence or even uniform convergence. Okay, so in this section we will develop a sense of convergence. Okay, so which will be called convergence in square adder, defined later. Okay. Now, since L2 AB, all right, has a semi inner product F G defined to be with respect to a weighting function okay, R of x on AB which is assumed in this section, okay, to be continuous on AB and positive in AB. Okay, so I think I have to correct my lecture notes. It's positive in this open interval, so it may be 0. Okay, it may be 0 at the endpoint. Okay, so the weighting function here is assumed in this section to be continuous on AB and positive in A and B. Okay, positive in the open interval, but the weighting function may be 0 at one or both of the two endpoints. Okay, so I think I have to make a correction. Okay. I have sent the lecture notes to you in the noon time. Okay, so Okay, so so L2 has a semi-long, a semi-inner product, and it has a semi-long okay, defined by to be the square root of the inner product of X with itself and with respect to the weighting function R. Okay, and the semi-norm has the following property. Okay, this property, of course, can be deduced from the property of semi-inner product we listed, okay, in section number 5. So for all f, g in L2 and alpha in C, okay, I'm sorry, one more either. Okay, so alpha is constant. 1, the norm, the semi-norm will be non-negative. And the semi-norm is 0 if and only if f is equivalent to 0. Okay? Means that f is 0 almost everywhere in the finite closed interval AB. Okay? First of all. Second, if we scale f by alpha by a complex number, then the norm would be the absolute value of alpha times the norm of f. Okay. And third one, we have triangular inequality. Okay. Okay. All right. So we have these 3 properties. Okay, and so from these 3 properties, then the semi-long of a function can be regarded as the length of f. Okay, so we can regard, we can define the length of a function, of a square integrable function, as the semi-norm. Okay, with respect to the weighting function R of x. And we define, so once we have length, so we define the distance, okay, between two function f and g okay, in L2 as the norm of the difference. Okay. Norm. So we can measure the distance between two functions. And you can see that if f and g are in the same equivalent class, means that if f is equal to g for almost all the points x in the interval, then their distance is 0. Okay, from here, on the first property. Okay, so they have zero distance. They have zero distance. So note that if f and g, if f is equal to g, i.e. f of x equal to g of x for almost all x in AB, if and only if their distance is 0. Okay. Any questions? Okay, that's good. All right, so now the following concept of convergence, okay, in L2 space is very useful in science and engineering. Okay, so I will state the definition here. A sequence of functions in L2. So means that each f sub n is a square integrable complex or real value function. Okay. Now such a function is said to converge, okay, to a function f in L2 in square adder on AB with respect to the weighting function of x if the limit of the distance the distance, so the limit of the square of the distance, which is going to say here it's 0. So the distance between f and the fn, well, goes to 0 as n goes to infinity. So when we have this limit, we say that such a sequence, right, converge to F, okay, in square adder, okay. So here we can see we have squared adder, right, and the integral over all x in the interval from A to B, weighted by, and the weighter is weighted, the adder is weighted by the weighting function R of x. Right? So this sense is that we regard the convergence as a whole function, right? So we regard each function as an object, okay? And so the measure of the distance of two objects or two functions, two square integrable functions, is represented by this integral. Okay. Okay, and the following theorem state that uniform convergence we studied in section 3. Okay, so the concept of uniform convergence implies, okay, convergence, right, implies convergence in square adder. Okay. Okay, so convergence in square adder is weaker than uniform convergence. Okay, so uniform convergence is stronger. So if you want to have a stronger result, then the function you specified must have a better behavior. For example, the function we studied may be continuous or continuous differentiable. Okay, so if the function is continuous differentiable on AB, then of course it is square integrable. Okay, and then if we have, by using the, for example, in the wire test, uniform convergence test, you will know that you can find, for example, the trigonometric series, Fourier series to converge it uniformly, right? And so that, but in L2, the function L2 may be wider, all right? They may not be continuous, right, on the whole interval. Okay, so we will see that with the concept of convergence in square adder, then we were able to prove some result of the convergence of functions in L2. Okay, but at least at first we will show this result, that uniform convergence implies convergence in square adder. All right, so this will be stated in this theorem. All right. So if such a sequence in L2 converges to a function f in L2, right, uniformly, okay, on AB, so then this sequence converges to F in square adder. Okay, so let's see a proof here. Okay. Oh, okay, I have to specify with respect to a weighting function. Of x. Okay. So now, so since Fn converge to F uniformly on AB as n goes to infinity, all right? Then for all epsilon greater than 0, there exists an capital N greater than 0. Right, so positive integer okay, such that f of x minus f of n over x, right, less than epsilon for all n greater than equal to capital N, and for all x in the finite cross interval. Okay. So this is the meaning of uniform convergence. Now, so that this adder, the bound of the adder, this epsilon is a common bound for all x. Okay, for all x in the finite cross interval. Okay, so that is the useful property. So now we look at all right, so we look at the distance between f and Fn with respect to the weighting function R. Okay, so we know this is of x. Okay, so it's this integral. But you know the square of the distance, all right, is less than square of epsilon. So that we can write here okay. For all, and this one is a constant. All right, so this one is a constant. Okay, so you can see that if you set epsilon to be small, then the distance become less than this small number, and so this is for all index n greater than equal to capital N. Okay, so this shows that Fn converge to F in square adder on AB with respect to the weighting function of x. Okay, so this shows uniform convergence implies convergence in square adder. Okay. So a question. All right, so does the generalized Fourier series generated by an f in the L2 space, okay, with respect to an eigen system right, of a regular, periodic, or singular Sturm Liouville problem on AB. Okay. Converge to f in square either on AB with respect to the weighting function. i.e. the limit n goes to infinity f minus x is 0. Where the xn of x is the partial sum function. Okay, so the question is here. So the convergence concept is different from the concept we studied in section number 1 and the section number 4, okay, where we consider pointwise convergence, our uniform convergence, okay, for all points in the finite closed interval A to B. Okay, here the sense of convergence is in square ether. So we will look at the distance, okay? So we look at. So we want to show. So the question is that once we have generalized Fourier series like that, and we know we have partial sum functions, okay, and these partial sum functions, okay, well, of course they have some distance, but the distance between the partial sum function and the function f goes to 0 as n goes to infinity. Okay. So we want to answer this question. So any questions about this question? Raised up here. Okay. So it is a weaker a weaker sense of convergence than uniform convergence. Okay. So maybe I can write a diagram. So uniform convergence. So in L2, all right, uniform convergence. This concept implies, so on AV, implies pointwise convergence on AV, and also implies convergence in square adder on AV. Okay. But but they may not imply each other. Okay. They may not imply each other, right? So you can find a sequence of function which converge to a function in square adder, but cannot converge in every point on AB. Conversely, you can find a function, a sequence of function which converge to a function pointwise, all right, for every point on AB, but not uniform. Okay, then this sequence will not converge in mean square. Okay, so you can't have any implication here. Okay. All right. So the concept we have deal with like is this concept. Okay. All right. So now to answer this question, okay. So we consider an arbitrary orthogonal set of functions in L2. All right, orthogonal set with respect to a weighting function Rx. All right, so the meaning is that the inner product of two functions in this sequence will be 0 for all n not equal to m. So they are orthogonal, right? And we will assume since 0 function will orthogonal to every other function, so we will assume that the length, okay, of phi n is greater than 0. Okay? In this section. Okay. So we'll consider non-zero orthogonal functions in this sequence. Okay. Okay, so now for a function in L2 space, the infinite series summation of n from 1 to infinity Cn phi n of x with coefficient Cn computed as the ratio of two inner product with respect to the weighting function R. Okay, so which is just equal to so the coefficient is defined this way. Okay, so for each square integrable function in the L2 space, we can construct such a infinite series. Okay, infinite series. So this infinite series will be called the generalized Fourier series. Okay, generated by f with respect to the orthogonal set. Okay, so now for any orthogonal set, okay, of course in here we use infinite orthogonal set to generate the generalized Fourier series for any square interval functions. And as we have learned from section number 5, any eigensystem of a stem durable problem can serve as such an orthogonal set, right? But here we just study arbitrary orthogonal set. So we consider the approximation problem to a function f in the L2 space by an arbitrary linear combination of the first n functions phi 1, phi 2, up to phi capital N. So we will approximate for a given capital N greater than or equal to 1, where D1, D2 up to D sub capital N are constant in C. Okay. Right. So we consider such an approximation. Okay, so this is the arbitrary linear combination of the first capital N members in the orthogonal, let's say. Okay, so Dn can be arbitrary, right? And so now the square adder, okay, the square adder of this n-term approximation, okay, it's En, which is just the square of the distance between f and the Tn. Okay, and so you can see that it's just the integral of the weighted square adder, right? And when you recall our study in section number 4, okay, in that section we consider the approximation of the functions in the trigonometric system. 1 sine x, cosine x, sine 2x, cosine 2x, etc., right? In that case. But in here, we consider more general case that the phi n xn orthogonal, let's say. So we can write it down here. And as you can see that with a similar derivation in section 4, okay, so with similar argument in section 11.4, we have, okay, we have that En En is equal to En will be all right, it's a low bound. Oh, okay, you can find that. All right, so this En is equal to so xn is the partial sum function, right, of the generalized Fourier series generated by x, okay, plus summation dn minus cn square. All right. So you can. I have written details in my lecture notes, but this is with a similar argument as we did in section number 4, that we can derive this equality. Okay, so the approximation by an arbitrary linear combination of the first n functions in the orthogonal set, this T sub n. Okay, the distance, the square of the distance is equal to the square of the distance between f and the partial sum function x7 plus a term like this one. And this term is expressed by the square of the distance between the coefficients dn and the cn okay, as well as the square of the length of each function phi n. Okay. So of course, we have this one immediately, and the equality holds if and only if dn is equal to Cn for all n greater than or equal to 1. So we have that. So the best approximation, all right, would be the partial sum function. Okay, would be the partial sum function. Okay, and we also know the difference is equal to the square of the length of function f minus the summation square. Okay, right. So we have this one. Okay, so now we can state theorem 11.6.b here. Okay, so for any capital N greater than or equal to 1, the best approximation in square adder with respect to a weighting function of x to a function in L2. Okay, by an arbitrary linear combination T sub n of x of the first n functions okay in an orthogonal set. Okay, is that so the base is that Tn equal to the partial sum function. Okay. Okay, i.e. dn equal to Cn for all n. And the minimum square adder En tilde is just the square of the length of f with respect to the weighting function minus a sum, all right, which is the sum of the square of the Fourier coefficients multiplied with the square of the length of phi n. Okay, so which is just equal to this one. So this is the best approximation we can have. So the results is basically the same results as we studied in section number 4. Okay, but here we study an arbitrary orthogonal set. All right, an arbitrary orthogonal set in the L2 space. Okay, and to get the same result basically. Okay, and you will see that this theorem plays an important role in answer the question we raised up here. Okay, so I will continue this study on Thursday. And any questions? Okay, no? Okay, so see you on Thursday.